I will be talking about fast dynamic algorithms for cuts, distances, and effective resistances using vertex sparsifiers. This is joint work with Chen, Monika Henzinger, Richard Peng, and Thatchaphol Saranurak. In dynamic graph algorithms, the goal is to come up with a data structure that maintains a graph which undergoes edge insertions and deletions. And at any time, the dynamic algorithm must be also able to answer a query about a pairwise graph property in the graph G. So in other words, we would like to maintain G either exactly or approximately, and we would like to also achieve small update time, which is the time to handle edge insertions and deletions, and small query time, which is the time to handle queries. There are many variants of dynamic graph algorithms studied in the literature, namely the fully dynamic versions, where you are allowed to insert both and delete edges. In the decremental version, where you're only allowed to delete edges, the incremental version where you're only allowed to insert edges. In this paper, we design many improved dynamic algorithms for graph-based optimization problems like maximum flow and shortest path. And we do this by introducing a general framework that allows us to design fast dynamic algorithms whenever the graph property we're looking at satisfies certain properties of interest or certain features. And this is all achieved by using vertex sparsification and their data structure generalization, which connect them to dynamic graphs. Many of the algorithms in this paper also satisfy the robustness requirement associated with dynamic problems. For example, the max flow result works against adaptive adversary, while the shortest path result it's deterministic. Let me tell you about vertex sparsification. So here the idea is that I'm given a big graph G where vertices are labeled with two different colors, namely black and red. And the vertices that I care about are the red vertices. And now the goal is to come up with a small graph H that retains the red vertices and at the same time preserves some feature or property of interest like maximum flow, distances, or electrical flows only among vertices that I care about, only among the red vertices. And these red vertices are widely referred to as terminal vertices in the literature. So the goal, of course, is to come up with a Sparsifier that has small approximation error or quality, and its size is also as small as possible. So this has been a very powerful tool in approximation algorithms and has been also applied to many cut-based and distance-based problems. And here I would like you to show how is this connected to dynamic graph algorithms. So why vertex sparsification? Why is vertex sparsification useful as a tool in dynamic graph algorithms? Well, we would like to come up with a few requirements what makes this object useful. First, it's important that the vertex sparsifier that we construct for the problem that we're looking at can be actually computed very efficiently in, say, nearly linear time. This is the first requirement. The second requirement is that we would like to update the Sparsifier whenever we insert a new terminal to the set of terminals, so to the set of vertices that I care about. So how efficiently can we update? So the underlying graph G remains the same, but how efficiently can we update the Sparsifier whenever I introduce a new terminal? This we would like to do efficiently. And the third property is that the graph property that I'm looking at, this pairwise graph property, must be decomposable with respect to the Sparsifier. What does this mean? It means that if H is a Sparsifier of G, and if I add an edge to the graph G, then H union E must also be a Sparsifier for the graph G union E. So when we started working on this problem, we already observed that just by looking at recurrence 1 and 3, so just by looking at static vertex Sparsifier constructions that are efficient and the decomposability property, you can come up with very efficient offline dynamic algorithms for problems like maximum flow and shortest path, which was kind of surprising, but also at the same time, the offline version is a bit weaker because it gives you the sequence of updates and queries in advance. Now the question is, can you actually generalize to the online problem? So can you use Vertex Sparsifier to design efficient online graph algorithms? So this is what we precisely do in this work. So we show how to design dynamic algorithms using Vertex Sparsifiers. And first, let me start telling you the incremental meta theorem, which is the simplest amongst all the meta theorems that we prove in the paper. So here we basically say that if recurrence 1 and 2 are implementable with Fn and Gn overheads in the running time, and if the property that we're looking at can be computed in m age of n time, where m is the number of edges in the graph, then there is actually an efficient dynamic algorithm which alpha approximates the property GUV with time, with update and query time m over b Fm plus beta Gn Hn. And you can get a very similar statement for fully dynamic graphs. I'm just going to omit it because I don't have time to go into details. So let me just explain in a few lines how the incremental algorithm works. So it starts by simply computing an alpha vertex Sparsifier of G, and then it computes this Sparsifier every beta operation. So we could recompute the whole data structure every beta operations. And whenever I get an edge insertion, I just declare the key operation here is that I declare the endpoints of this edge to be terminals in the Sparsifier edge. So once they are terminals, then I simply add the edge to the Sparsifier edge. Similarly, when I have a query between which involves like two vertices, for example, the query could be what's the shortest path between S and T. So I take S and T and I declare them as terminals, and then I just put them so I just put them as terminals in H and then compute the answer in H. And by this, by this simple algorithm, you can show that the following trade-off claimed in the incremental meta theorem can easily be achieved. So what are other applications of this technique? Okay, so let's be more specific. Let's replace this problem PGUV with specific problems. So here, for the fully dynamic algorithms, we get new algorithms for the maximum flow problem, which is one of the cornerstone problems in combinatorial optimization. So we get the first sublinear algorithm, which achieves a logarithmic approximation with update and query time being n to the 2/3. And we also improve by a polynomial factor the best known upper bound and effective resistances. While for incremental algorithms, we show that for the all pair shortest path problem, there is a dynamic algorithm that achieves a very large constant approximation, but with very small polynomial update time. And this algorithm is deterministic, so it doesn't use any randomization. And it's based on the oracle by Thorup and Zwick. And the main observation is that this oracle can be viewed actually as a vertex distance Sparsifier. So unfortunately, I will not be able to explain everything here, but I will try to convey a few ideas behind our maximum flow result. And let's do this. So as I said before, max flow has been extensively studied in theoretical computer science and algorithm design, and there are still papers being published on this. Unfortunately, the dynamic version of max flow has been very poorly understood. So there are a few works where I either consider special family of graphs or consider bounded connectivity. For example, for planar graphs, there is the work of Italiano and others, which achieves sublinear time, but it's only restricted to planars. And there are a few more other works where they work for general graphs, but then we have this problem that we are only looking at incremental algorithms. So our work is the first to get the fully dynamic algorithm and achieve a nearly logarithmic approximation to maximum flow, to maintaining the value of maximum flow. And we can do all this in sublinear time. And the time here is like n to the 2/3. So there is a concurrent work to our work. So basically, which me and Thatchaphol are also involved, where we actually got a fully dynamic maximum flow algorithm with subpolynomial approximation, but the running time is also subpolynomial. So in a sense, basically our works achieve better approximation and their works achieve, the other work achieve better runtime. So the whole idea of doing dynamic max flow and everything is based on this powerful tool in static graph algorithm called tree-based graph approximation. So the idea is very simple. I'm given a graph. It's very complicated. I don't understand it. I want to approximate it by a tree. And I lose something when I approximate the graph by a tree, obviously, right? And then I take the tree and I solve the problem on trees, and graph problems on tree are usually easy. And then I translate the solution back to the original graph. So this is the idea that usually it's very used in algorithm design, right? So the ultimate goal, like in the research theme that I'm trying to follow here, is that can we actually make this construction dynamic? Can we maintain this tree-based graph approximation dynamically? And let's start explaining a bit what are these tree-based graph approximation. And a very powerful one is the one by Recke in 2018, where he shows that for any graph G, one can find a convex combination of trees. So no, this is not a single tree, but he can find a convex combination of trees or spanning trees such that for any cut S, the value of the cut in each of the trees is dominating. And on average, the cuts are preserved up to a logarithmic factor. So an average means here, I go in each tree, I find the cut, and then I weight according to the convex multiplier, right? So this is how you take the average. So this is a very powerful tool and has been applied extensively in approximation algorithms. Unfortunately, the running time is at least quadratic in a number of edges. And here we are talking about efficiency, so it's not good enough for us. So fortunately, there is this more work of Madri, who said that, well, I don't want to approximate graphs by trees, but I want to approximate with more complicated objects. And these more complicated objects are called J trees. So let's look at what a J tree is. So the idea is, I don't want to approximate G with trees anymore because it's somewhat expensive. Let's allow more complicated graphs, but of course, these complicated graphs should be simpler than general graphs, right? So more precisely, Madri said that a graph is a J tree if it can be viewed as a union between a forest, F, which is called the envelope of H of the J tree, and an arbitrary graph C, which is called the core of the J tree. And there are two important properties here of J trees. The first one is that the number of vertices in the core is bounded by J. And the second property is that each tree in the forest contains exactly one vertex in the core. Okay? And one can easily observe that a one tree is a tree, right? So then Madri came up with this similar decomposition or convex combination of J trees, which is very similar to what Recke had. But then he showed that basically I can trade off, I can obtain a trade-off between the running time. So his running time reduces with J, right? Is m squared over J. And I can get a convex combination of J trees now, and not trees anymore, such that cuts are preserved in expectation up to a logarithmic factor. So there are two useful properties that make J trees very appealing from a dynamic point of view. The first one is that you can just sample log n J trees, and by just sampling log n of them, you actually preserve all pair mean cuts up to log n factors. So you don't need to maintain the whole trees in the decomposition. Once you have constructed decomposition, you just sample log n of them. And another useful property is that J trees can be viewed as vertex sparsifiers. Recall that a J tree consists of a forest and a core. So the core corresponds to the terminal vertices, or can be thought as corresponding to the terminal vertices. And then you can compute the cuts in the core and then basically expand this cut to the set V by just attaching parts of the forest F. So in this paper, we show that J trees can be viewed actually as vertex sparsifier and can be made to support the operation of adding terminals to the J tree, right? So in other words, so given a graph G and a J tree H, we show that there is a data structure that maintains a slightly larger J tree that approximates the graph with similar guarantees to how H approximated the graph. And more importantly, we show that the running time for adding a terminal to the graph H prime is bounded by Mn over J squared, right? And by adding a terminal here, I mean, I take a vertex which is not really a core and then I move to the core. So remember, this is a requirement 2 from when we try to convey when is a data structure useful to construct dynamic graph algorithms. So we show that the requirement 2 can be actually efficiently implemented when we talk about J tree and cut approximation. Another important thing is that the core of the J tree that our algorithm maintains is relatively sparse. So it has roughly J edges at any time. And another thing to remember is that this theorem works as soon as you allow J operations, right? Because I want to maintain, because I want the size of the core to be roughly J, okay? Unfortunately, this will work only against oblivious adversaries, but then we can show how to make this work against adaptive adversary. But I'm not giving you any details here. So because it was kind of impossible to now review the construction of Madre and show how to modify it in this limited amount of time, I'm just telling you the main ideas behind our construction. So basically, we white box the construction of Madre, where we also ensure a few more structural properties about J trees. For example, we say that any vertex in the graph in the J tree, it cannot be very far away from the core, and we can ensure this accordingly. And another important observation is that when you add vertices to the core, when you add these terminals, the quality of the J tree can only improve as a sparsifier of G, and this is actually very important. And because of adding vertices to the core, the way how the embedding works, how we embed G into the J tree can be messed up, because there might be edges incident to the vertex now that is a core vertex, so they need to be rerouted accordingly in the J tree. So we also show how to do this efficiently. And the last idea that we have here is that the core can be dense, because remember, it had J vertices, but it can have up to J squared edges by construction. So we maintain a sparse representation of the core. And to achieve this, we maintain a dynamic S-sparsifier. So now this is not a vertex, so this is a S-sparsifier. So we maintain a dynamic S-sparsifier. And fortunately, we know that we can maintain such objects due to the work of Abraham et al. In 2016. And yeah, this is basically the construction. So now once we have this J tree result, and we can add terminals to J trees, the fully dynamic algorithm for max flow is very easy. So what it does, it starts by computing a J tree based approximation for cuts, and this you do by Madre's algorithm and our modification. And then you sample log n J trees from this distribution. And for each of them, you maintain our data structure, which allows you to insert terminals as the data structure runs. And then you recompute this every J operations. So now, whenever an edge is inserted or deleted from the graph, you take the points of that edge and you include them as terminals for all the J trees that you maintain. Okay? And then you also take that edge and either insert or delete it, depending on the operation, from the core of each J tree that you maintain. Okay? So this is very simple. Whenever you have a query that says what is the max flow between S and T, you add first S and T as terminal vertices in each of the cores. And then in each sparse core that you maintain, now the sparse one, not the original core, you compute the ST min cut between S and T. And not, because I added them as terminal, S and T are now contained in the sparse core of each J tree, right? And you return the minimum amongst them. And then by the lifting property that we show, this actually ensures that you get the log n approximation. And just bringing together all these running times, so m squared over j, this is the running time required to construct a J tree based decomposition by Marjorie, and this is the running time for inserting or deleting a terminal. And the query is simply J because we always compute on the sparse core. We get the following trade-off, which is minimized at m2/3. So we get an m2/3 running time. And we can make this an n2/3. So get what I promised you in the beginning by simply running the algorithm on a cut sparsifier initially, okay? On a dynamic edge cut sparsifier. So let me summarize. We showed the general framework for designing sublinear dynamic approximate algorithms for graph-based optimization problems, and we showed that important problems that are at the core of algorithm design, like maximum flow, shortest paths, and random walk-based similarity scores, such as effective resistance or commute distance, can be maintained dynamically using this approach. And there are obviously many open problems from this work. For example, we don't know how to improve the approximation factor of our dynamic max flow algorithm. Right now, it's at log n, and this is tied based on the approach that we took. It's essentially tied because you need log n approximation to approximate graphs by trees. And we also don't know whether there is a multi-level version of the dynamic max flow algorithm. So right now we are stuck at 2 levels. So we don't know whether we can basically recurse on the J tree further. For example, Marjorie in the static setting could do this. And there could potentially be other problems that can benefit from our algorithm paradigm. For example, one can look at LP norm minimization. But more importantly, because we showed this tight connection between Vertex sparsifiers and efficient dynamic graph algorithms, it's kind of embarrassing that there is no progress for the question of whether there is a Vertex sparsifier that preserves terminal cuts with 1 plus epsilon approximation and any polynomial in k, where k is the number of vertices and epsilon is the approximation error, right? So we don't know whether this problem is basically solvable now, whether this is true or not. So, and it seems like it's a core problem related to many other areas in algorithm design, and I would like to see more progress on this or more work on this. Okay, thank you very much.